Before I start, I should apologize for the redness of this slide. The reason is that after this defense is done and I've rewritten the thesis, I would like to have it printed in a little booklet with a bright red cover for two reasons. The first is that I could then quote the great Oscar Wilde, who wrote, "When I am gone, I hope it will be said, my sins were scarlet, but my thesis was red." But the second reason is, of course, that red is the color of passion, and passion is the word that throughout the history of philosophy was used to describe the states that drive these actions. And great philosophers like Plato believed that there were virtuous passions in addition to corrupt ones that can drive our action. And people like David Hume and Baruch Spinoza quite agreed with them, and they were quite strong advocates for the study of passions to understand behavior. But in contemporary psychology, we don't talk about passions, we talk about affect. And so today I will give you a computational account of how affective states influence economic decisions. And so the question that you can ask is it irrational to let your emotions influence your behavior? An advocate that was quite outspoken about this view is Descartes. He definitely believed that emotions corrupt reason. And that passions are these things that influence the soul through corruption of the pineal gland to make it desire all sorts of undesirable things. But the opposite view was that of the Darwinians, who believed that we've evolved to be these complex, sophisticated species that have emotions, so they must serve some adaptive purpose. Quite famously, Antonio Damasio formulated the view that emotions can actually help us make appropriate choices. And so this notion of affect and rationality will be one that I'm going to give a little bit more background of as I introduce the talk. I'm then going to tell you about 3 empirical studies that I've done throughout my PhD, where we will find an affect bias in behavior that will come back at every time. I'm also going to highlight a method that I developed that helped us find this effect. And I'm then going to formulate a theory that we came up with to account for why this affect spillover onto decision-making could happen. So I'm going to zoom in briefly on specifically economic rationality. In the past century, there's been quite a bit of development on this, on work from von Neumann and Morgenstern on how, on game theory and on how the rational economic decision maker should behave. And the maxim states that you should maximize your expected utility. And also, when you're faced with the same decision multiple times, you should not fluctuate, you should always behave coherently. From this point of view, you can already see where I'm going. Emotions could be quite irrational. As a matter of fact, economists have accounted for this. They've formulated reasons why humans are bounded in their rationality, and there were more than one Nobel Prize winners who've said that it's emotions that, at least to some part, contribute to this boundedness of our rationality. There's plenty of examples of this in the real world. For example, when the stock market when the weather is actually nicer than expected, the stock market returns are a little higher as well. Or when the country's soccer team was just eliminated from the football cup, from the soccer World Cup, as was the case for, I think, everyone present here, unless we have Argentinians, then stock market closes a little lower. And also it was found that not only on the whole economy, but also at the individual level, when the weather is nicer, when your local baseball team has just won, people tend to buy more lottery tickets. So there's definitely this real world spillover from emotional events onto people's decision-making. And clearly this causes people to fluctuate in their decision-making, which is irrational. And clearly these influences have nothing to do with maximizing expected utility. So from this point of view, yes, emotions are irrational. We're going to use this framework of economic decision theory to precisely look at the subjectivity that I talked about. So you can model people's subjective preferences as a function of their reward and costs. And we're going to use that framework to quantify the impact of emotions. So let's get started again with this example of gambling. This is an example of how we show gambling decisions to our participants. So this is a screen where we offer a risky option where you can win 30 euros, a fixed large amount of money, but you can also lose 10. And the risk of losing 10 is proportional to the area that is shaded in red. The alternative is to take a safe option that you are 100% guaranteed to receive the alternative amount of money that is always lower. So you could, if you are a rational economic agent, calculate the expected utility of either option and choose whichever one has higher expected returns. But people don't typically do this. So here you see an ensemble of discounting functions, as we call them, that describe the subjectivity of people's decision preferences. And as you can see, people fluctuate on the spectrum of being more risk-seeking or more risk-aversive. These are actual data from one of our studies that we did. And the maths are not super important for now, but what it shows is that as a function of reward and costs, people differ in how they discount money as a function of cost. This was also true for delay, where people are faced with the possibility to receive a large amount of money after some delay. In this case, it was a calendar that showed you that you had to wait 9 months and 1 week, or alternatively, you receive a smaller amount of money immediately. This we modeled as a hyperbolically decaying function, I should say exponentially decaying function, that asymptotically inclines to zero, with the idea that if you receive 30 euros in 25 years from now, it doesn't matter anything to you. We applied the same principle to effort. In the first instance, physical effort, where you're offered the choice to get a large amount of money for climbing a certain amount of flights of stairs, or alternatively not having to do any effort for a lower amount of money. This was modeled with a parabolic decay function that notably can be negative. And the same was true for mental effort, where people were offered the opportunity to copy pages of text in a non-existent language. This is quite mentally effortful for a large amount of money, or again, not do that effort for a lower amount of money. So again, a parabolic decay function. As I said, the maths are not necessarily important here, but what I want to show is that with two simple parameters, a weight on reward and a weight on cost, we call that a discount function, discount factor, you can describe the subjectivity of people's preferences, and you can get an expression for how people evaluate these options. So applying economic decision theory, you can get the subjective value of either option as a function of reward and cost. The decision value then is simply the difference between the value of the costly and the uncostly option, which you can plug in to a choice function. We use a softmax function, a sigmoidal decision rule, that expresses the probability of choosing the costly option on the spectrum from 0 to 100%. There's one parameter in particular that I would like to highlight because it's going to be especially important to us today, and that is this bias parameter. So this sigmoidal function, if it were unbiased, it would predict that if your decision value is 0, which means that you are exactly indifferent between the two options that are being presented, your choice probability should be at random, should be 50%, because you're exactly indifferent between the two options. They both mean equally much to you, so you can choose either with the same probability. But it is this bias parameter that governs a predilection to choose either the costly or the uncostly option. And the reason I'm telling you this is that we're going to find an affect bias parameter in the 3 empirical studies that I'm going to talk about today. And for now, I'll zoom in onto the first one. This is a project that I did in collaboration with fellows from my team, and it was data collected by my colleague Pablo Carrillo, based upon an experiment originally developed by Fabien Venquier. In this study, with just over 100 participants, people do a quiz task. That's what Fabien developed, and a choice task, and that's my contribution. So people make decisions on, actually, I'll zoom in onto a single trial first. So what does this quiz task entail? You start off with a quiz question that's being presented to the participants, and then 4 possible answers, of which the participant chooses one. Let's say that the participant makes the right answer. Then they get positive feedback, which was a smiling emoji and a ping. Or they could get negative feedback, which would be a frowning emoji and a buzz. They then rate how they feel on a mood scale. And then they make one of these 4 types of choices, decisions with one of these 4 types of choices that I talked about. Now, unbeknownst to the participant, there's 2 sneaky manipulations. The first is that actually at a base rate of 25% of the cases where participant gave the wrong answer, we actually tell them that they gave the right answer. So they get more positive feedback than they actually should get. But we create episodes in the course of the experiment where that feedback bias goes up to 50%. but it can also go down to 0%. So there's cases where in 50% of the cases where you give a wrong answer, we tell you that you had it right. Or in every time you get a question wrong, we will tell you that you get it wrong. Now, the questions were quite difficult, but on top of that, we also made the questions extra difficult in the negative episode and a little bit more easy in the positive episode. So what you end up with is fluctuations throughout the experiment where the participant undergoes lots and lots of positive feedback, feeling really good about themselves, and negative episodes where the participant feels particularly bad about themselves. So the first thing to look at are these ratings that people give. And indeed, between the dotted lines, you see the duration of an episode of 18 trials, and you can see that mood starts to diverge. So in positive episodes, people feel better, and in negative episodes, people feel a bit worse. And then, of course, the big question is, does this mood, this rated mood, spill over to choices that people make here? And the answer is yes. And this is the take-home message for today. This is a result that's going to come back multiple times. In positive episodes, where people feel positive moods, there's an increase in the choice of costly but more rewarding options. Conversely, in negative episodes where people feel a little bit worse about themselves, there's an increase in uncostly but less rewarding choices. This was the case, at least trending or significantly, in each of the 4 types of choices that we, types of costs that we presented. So I pooled them together, and you can see this overall grand average difference that was very significant. Moreover, if you look at the response time specifically of the costly options, you see that people are faster to select them when they are in a positive mood state than when they are in these negative episodes. But these are just averages. These are what we call model-free analyses. So you can also fit a choice model that we talked about earlier. And then what you see in the psychometric curve is that there's a vertical shift between the choices made in the positive episodes and those in the negative episodes. So what this shows us is that if you take the residuals from the predictions of the model versus the observed choices that were seen in the experiment, the residuals are actually quite robustly correlated with the rated mood that people give, their mood rating. So we were inclined to adapt the choice model that we have by adding a mood bias parameter. This mood bias parameter could account for the shift in cost-benefit trade-offs, and it was highly significant. We believe that the reason why we succeeded in getting this particular result was that we made our experiment very precise and very sensitive. And we did so with online trial generation. And this is a method that I developed that is based on online trial generation that I'll now elaborate on just a little bit as a side note. Online trial generation is the idea where you generate trials not before the experiment, but during the experiment. Typically in psychology, this is not done. The reason we did it during the experiment is that you can then have the freedom to select those trials that will maximally be informative for your experiment. And we believe that when participants are indifferent between the 2 options, that's when they're going to be most sensitive to the impact of mood. It's easy to see that if one option is clearly a lot better than another, a little bit of mood is not going to swing you and make you change your mind. But if you are roughly equivalent, if the 2 options are roughly equivalent, then mood could quite make the difference. So we had an interest in presenting choices that people were indifferent about, but people differ in their indifference curve. And so we want to have an experimental design that is optimized by getting an accurate estimation of that indifference curve. And so we do that by updating our model estimate with every choice that the participant makes. The problem that people typically run into when they do this is that you have to pre-commit to a certain model, for example, a hyperbolic decay function or a parabolic decay function. And we did not have very strong priors about the shape of the curve before starting the experiment. And so we came up with a solution that we call the multilinear function, where we break down the cost spectrum into 5 bins and form a local linear approximation of the participant's indifference curve, so that after just a few trials, our algorithm can adapt to virtually any shape of an indifference curve that the participant might have. And so you don't have to pre-commit to a certain shape. There's a second benefit, and that is that you can calculate the area under the curve quite easily, and that number, that area under the curve, is a very good momentary readout of people's preferences towards choosing costly options. I'm now going to give you an illustration of how this algorithm works. So what you can see on the right is an illustration of the choice screen that the participant faces. You can see an actual human participant, me, making choices between delayed options for large rewards, or alternatively immediate options that are less rewarded. And so with every choice that the participant makes, our indifference curve estimate is updated. And with every updated estimate of the indifference curve, a new trial is sampled from that curve. And so in doing so, there's one major benefit, and that is that online trial generation is very useful for tracking slow changes in preferences over time, which is typically what's happening when mood fluctuates over time, right? So applying this to the previous experiment that I talked about, you can indeed see that the area under the curve gradually decreases in negative episodes and gradually increases in positive episodes. But there's a different, very convenient application of online trial generation as well, and that is that you can quite efficiently and quickly get an individual phenotype of a participant. That is, you can quite quickly get people's individual indifference curve, which is useful if you want to compare participants to each other or to themselves with some cognitive experimental manipulation in between. And so I've been fortunate to be involved in collaborations where I developed protocols for others, so not my main study, who studied, for example, fatigue in glioma patients, or in ultra runners who've just run a very mentally fatiguing marathon, or in depressed military patients whose symptom improvement was correlated with the average area under the curve increase after 4 weeks of antidepressant treatment. So this was just a side note to talk about the algorithm that I developed. Going back to the bigger picture, we talked about how slow mood fluctuations can impact decisions. But we also wondered whether we can induce some immediately affective state that has an immediate effect on the choices that people make. So not these slow drifts of episodes where people are, for some amount of time, more prone to choose one option or the other, but an immediate effect of the induction. And so in this line of studies, there were 4. We induced emotional states, affective states, I should say, with happy and sad text vignettes that were presented to the participant on screen, combined with instrumental music. There were also neutral inductions where the text was more encyclopedic and there was no music. I'm just going to give you an example of a happy induction. There we go. So this would be an example of a sentence that would be projected on the screen that the participant sees for 10 seconds. They read the sentence, they imagine the scenario, and they listen to the music. The music then keeps on playing while the participant makes a series of choices. These are the same types of choices that we talked about earlier, involving risk, delay, or physical effort. After those choices, people rate the emotions that they felt, and this timeline of a single trial was in the order of about 1 minute. And so the entire experiment consisted of a whole sequence of these trials that were counterbalanced, and so we're not having the purpose to ramp up some mood state, but were very short affective state inductions. We did this in 4 versions, 4 studies with a total of just under 100 participants. Now, the first thing to do when you do an experiment like this is validate that you actually succeeded in inducing an emotion. And the first thing to look at would be the ratings that people give. So the subjective ratings were unambiguous. When we present a happy induction, people rated that they felt happy. And when we present a sad induction, people rated that they felt sad. During a neutral induction, people didn't rate feeling much at all. But we wanted to take this a step further. So we took physiological recordings of arousal during the presentation of that emotion-inducing stimulus. And the first one on the left here is pupil dilation. And on the right, skin conductance. And the thick colored lines on top of the plot show you where, with random field theory, there is a significant difference between the emotion conditions and the neutral state. So what this shows us is that we indeed succeed in inducing some change in an internal state during our affective inductions versus a neutral induction. We then took the same approach that we took before, the dimensional approach, where we don't necessarily compare categories, but we want to use a continuum. And so we define what we call a mood score as the rated happiness minus the rated sadness, very simply. This term mood score might be a little bit contradictory or controversial, I should say, but we use the term because of two properties of mood, namely that it can be positive or negative and that it can fluctuate, which was the case here as well. And so unsurprisingly, mood is positive in the happy inductions and negative in the sad inductions. But taking it again a step further, we also recorded physiology, and in particular EMG of the smiling and the frowning muscles. So here you see the zygomaticus activity and the corrugator activity, and we recover this valence effect in people's micro-expressions, because every time there was this significant difference between the happy and the sad inductions. So we do believe that with the ensemble of this, we succeeded in inducing an affective state, an arousing, valenced state. But then again, the question is, did we succeed in also capturing an effect on choices? And again, the answer is yes. So I'm going to immediately pool the three types of costs together and show you this grand average, which has the same conclusion as before. The costly option choice rate is higher when we induced happy emotions versus following happy inductions, I should say, compared to when we present sad inductions. And again, also response times were slower to take the costly option when people were sad versus faster when they were happy. Following up on, no, I should add one thing. Actually, in this study, we also aimed to induce anger and fear as other emotional states. And I think we did succeed in inducing those internal states, but we did not get an effect on behavior. So we abandoned those emotions after the first two studies. Moving on then to the model-based results, we see again this vertical shift of the cost-benefit trade-offs in the sigmoidal psychometric curve. We again get a correlation of the model residuals with that mood score that we defined. And in each of the 4 studies we did, we could recover a significant mood bias parameter that overall was a very significant effect. So we reproduce the effect that we saw in the previous studies where affect is induced slowly, in this particular study where there are immediate and short affective state inductions. But all these results are results of rated moods. And we wanted to see if we could take it a little bit further with the physiological recordings that we took, so that they wouldn't just serve as a validation of the induction, but actually also to maybe predict the choices. So we constructed an arousal signal that was simply the average of the dimension-reduced skin conductance and pupil response, and a valence signal that was the difference between the zygomaticus and corrugator activity. Then we could construct this physiological mood signal that by multiplying those two and correcting for the trial number since the induction. And this physiological mood signal turned out to also be predictive of choice in the sense that they were correlated with the residuals from the choice model. Moreover, the regression weight of the physiological mood proxy in predicting these residuals was correlated with the regression weight from the rated mood in predicting those same residuals. So this is suggestive of the idea that they might capture related constructs. I want to get back at the mood bias for a little moment that we talked about before. So this mood bias is a predisposition to choose either one or the other option. And we wondered whether this predisposition would also translate in a predisposition. This predisposition to choose would translate in a predisposition to also preferentially pay attention to one or the other option. And so we did eye tracking for that purpose, specifically during the first second of presentation of a choice. So on the left, you can see an example of a choice screen as it would be shown to the participant. And on the right, you see the distribution of gaze during the first second of presentation on the screen. In particular, you see a difference map between the happy and sad inductions. And so what you can see is that indeed, there is this initial predilection to choose to look at the costly option when happiness is induced versus the small reward when sadness is induced. So you can start to see that there is this coherent image, this coherent message that starts to form where you're biased in the sense that you have a predisposition to choose one or the other option, which corresponds to what you preferentially pay attention to. And particularly for the larger costly option, you're also faster to choose that option if you're in a good mood versus when you're in a bad mood. this predisposition to choose one or the other was every time shown in these two-dimensional binary choices, as you see on the left. And you could also argue that it would be a good thing to have a little bit of variability in the sort of choice paradigms that you use. And so I'm very briefly going to talk about a side project that I did with master students India Pinhorn and Michael Lalou, which we called the Treasure Island task. In this experiment, we had the same emotion induction procedure as I showed you just before, but the choices were different in the sense that we turned it into a game where people choose between a small island associated with a fixed small reward or a large island where you could get a lot of reward, but you'd have to endure a delay in the sense that your boat had to reach the island first. And then you had to do an effort where you had to squeeze a dynamometer before the agent could climb up the mountain. And then you had to endure a risk in the form of a battle, an animated sword fight with the pirate. This might be a bit of an awkward description that I'm giving now, and I do have a video of this. So if the jury is interested in seeing that, then I'll be happy to show it afterwards. But for now, I'll just jump to the conclusions, which are that we did recover the mood effect on choosing the costly option, the large island. And we again saw that people were slower to choose the large island when they were sad versus when they were happy. So coming back to the bigger picture that we talked about, so far, everything I've shown you was were results that we obtained in very strictly controlled experimental conditions in the lab. And you could argue that maybe people behave differently when they are in the comfort of their own home or in the real world, not under experimentally controlled conditions. And so this last study that we did was entirely run online. We had just under 120 participants who, in a first phase of the experiment that we'll call the main experiment, did something that was pretty much exactly the same study as what I talked about in project number 2. So there were presentations of emotionally relevant vignettes with music, and people made these binary choices that we're familiar with and gave ratings. And just to be very brief about the results, just to show you that this experiment was a sequence of inductions, and that in total it took about 45 minutes. So these 119 people did this 45-minute experiment online in February of last year. And now I'll talk about the results. In terms of ratings, it was an exact reproduction of the pattern that we saw in the lab. So people rate feeling happy when we induce happiness, and people rate feeling sad when we induce sadness, and so forth. Also, in terms of the effect on decision-making, the effect was present in each of the 3 cost types, but I've pulled them together here. So it was this grand average significant difference between induced happiness and sadness in choosing the costly option. People were faster to choose the costly option when they were happy compared to when they were sad. And also when we do the model-based analyses, we again see the shifts in the psychometric curve. We see the correlation with the residuals, and we see this very significant mood bias parameter. But this was not actually the most interesting part of the study. It was phase number 2 that was more interesting, or just as interesting, of course. And that is that after those 45 minutes of the initial study, we invited people for the 6 months ensuing to take part every week in a 5-minute follow-up session where they logged in and rated their mood, their fatigue levels, and their stress levels. And they then did a short choice battery of 45 choices that took them about 5 minutes. And so for approximately 6 months between February and August, the participation rate was quite high. So during the period of time where everyone was enrolled, there were at least 90 weekly participants every week. So that was good. And what we also saw is that as the seasons changed, mood slightly improved and fatigue slightly declined. And now the big question is, do these real-world moods have an effect on decision-making? Let me be clear here that there's no mood induction or emotion induction procedure here at all. This is really people's real-world moods as they were feeling on that particular day. And indeed, we do recover the effect. So when people are having a good day, when they're feeling in a good mood, they indeed were again more prone to choose the costly option versus when they were in a negative mood and they chose the uncostly option more often. The opposite was the case for their rated fatigue, which curiously is a beautiful reproduction of the work that was previously done in our lab by people like Antonius Wieler and Bastien Blin. But focusing as we do today on the bias of mood, this follow-up session mood bias was again highly significant. And interestingly, it was correlated with the mood bias from the main experiment. So we could predict how sensitive people were in their decision-making during real-world mood episodes, as predicted by how they felt during, how they responded to our emotion inductions during the main experiment in phase 1 of the online study. So, putting all of this empirical work together, we are now in a position to claim that there is a robust mood bias effect in the general population that we've shown with multiple ways of inducing emotion or mood and in different choice paradigms. But the remaining question is why? We've recently formulated a theory where we take a bit of an evolutionary approach, where we're going to look at how our evolutionary ancestors, perhaps a very simple mammal who lives in a very simple world, would go about foraging its environment under the influence of mood. And that will be the last project I'll talk about. This is a theoretical study, so it's only entails simulations that I've run. There's no empirical data. And it's a theory that I developed together with Matthias, and that Matthias wrote up in a review article that is currently under review for publication. We co-authored it with Jean and Fabian from our team. So let's take the perspective of this very simple mammal ancestor of ours who lives in a very simplified environment where the only two edible properties of the environments are edible plants and prey. And so the only two actions that this agent can take is forage for edible plants and hunt for prey. Now, an idea that we borrowed from Aaron Eldar and others is that the reward distribution of these two actions fluctuates in the environment. And specifically, we were interested in fluctuations over time. So we simulate the behavior of this agent as rewards and costs associated with each action fluctuate over the course of 2 years. And so every day of those 2 years, our agent makes the decision to select action 1, select action 2, select both, or select neither. Different environments have different reward cost statistics. And so as you can see here, for example, the value of edible plants fluctuates over the course of time, where you get these summers where there's lots of edible plants and the cost of finding them is low. And in winter, there's fewer edible plants and you have to make more of an effort to get it, like your Brussels sprouts. Same for prey. So there are seasons where there's more prey around, and there's seasons where there's fewer and you have to make more effort to get them. So the net value of the two actions in the environment fluctuates over the course of time. And this is where our theory starts. There are 3 key properties. The first is that our agent, by going out and foraging for those 2 rewards, learns the momentary value of either action through a simple reinforcement learning rule that many cognitive scientists are familiar with, and then updates its mood. And we define mood as the global average of the 2 actions, or of any action that is present in the environment, but in this case there were 2. So mood is a momentary readout of how valuable you think your environment is. So in summer, when prey and plants are abundant, you're in a better mood than in winter. Then you can kind of see where I'm going with this. So you can imagine an agent that makes that action selection decision as a function of its momentary estimates of the reward and costs of either action, but that is biased by its mood in its decision, in its stochastic decision process that is exactly the same as everything we talked about before. Now, we're going to give 2 examples where we're going to compare 2 agents. The first is a cold agent, and the second is a flexible agent. The cold agent does not have any mood at all, so 0. So it doesn't have a mood bias effect. This agent fluctuates in its probability of selecting action 1 and action 2 over the course of time as a function of its learned value of selecting actions 1 and 2. But now let's compare this to a flexible agent who does have a mood, who updates its mood as a function of the value of the environment, and who is biased by this mood in its decision-making. What you can see is that this agent goes through periods of time where it's much more likely to forage when rewards are abundant, and much less likely to do so when the net value of that action is lower. And so in this particular case, if you make up the totals after 2 years of foraging, what you end up with is that the flexible agent is the only one to have a mood, obviously. Its foraging is similar, but the flexible agent ended up getting much more rewards and much fewer costs. And so that its balance is actually higher than that of the stable agent, the cold agent. So in this particular example that I gave you, we're dealing with a flexible agent that is biased by its mood, who does better than an agent who is not biased by its mood. And so in this example, you could argue that it's adaptive to be influenced by your mood in your decision-making. But now let me give another example. Again, we're dealing with the same cold agent who doesn't have a mood and who fluctuates mildly over the course of time in his foraging decisions. We're comparing it to a flexible agent who also goes through a high mood state during summer, but then as winter comes, the net values decline and it plummets into this depression, if you will, that it doesn't leave from. And that's because its probability of choosing actions in summer is very high. It's actually, you could say that it's manic in its foraging, but then as its probability of selecting the actions in the environment decreases, it is so biased against foraging that it will never leave its cave again and will miss out on the change of seasons and on the propensity to find rewarding options in the future. So it remains stuck in this depressed state. And then if we make up the balance after we compare the totals after 2 years of foraging, what you can see is that on average, this flexible agent actually has a negative mood. It forages way less than the cold agent. And most importantly, it ends up with a lower balance. So in this case, it's clearly maladaptive to be influenced by your mood in your foraging decisions. And this begs the question, under which conditions is it adaptive and under which conditions is it maladaptive to be influenced by your mood? The first answer to that question is that it depends on the parameters of the agent. To give you a spoiler, in the first example, I gave a mild mood bias, and in the second, I gave a very high mood bias. So as a matter of fact, the agents that we defined can be, in its simplest form of the model, defined entirely by only 2 parameters, learning rate and mood bias. So if you systematically make combinations of learning rates and mood biases and you simulate hundreds of environments, you can make these contrast maps between cold and flexible agents, where you can see how different they are in terms of their mood average, their foraging behavior, and interestingly, in the balance of their foraging totals that they end up with. As you can see, there is a global maximum. That is to say that across environments, there is a combination of learning rates and mood bias where you actually are best off having a certain amount of bias from your mood onto your decision-making. In this case, you outperform the cold agents most of the time, if not always. But that's only part of the story. The adaptiveness of mood also depends on the statistics of the environment. And again, this is where the story of Aaron Elder comes in. So the performance of the various agents can be compared across environments, but also between environments. And here I've grouped environments into how autocorrelated they are. That is to say that if an environment is very autocorrelated, the value of the environment today is predictive of the value of the environment tomorrow. Now, that's an essential feature because if that's the case, then it makes sense that you're biased by your mood. But if it's not the case in an autocorrelated environment, having a mood bias has no benefit at all. The same is the case for the correlation. My computer's freezing. The same is the case for the correlation between the 2 action values, where, there we go. The 2 action values, because if they're uncorrelated, there's no reason to be influenced to have an influence from one action over another. But if there is a correlation between the 2 action values, then it actually makes sense to have a mood spillover. So if your mood is enhanced because of the values you encounter from one action, if that is also indicative that the other action is also valuable, then that means that they're correlated. And then in that case, it also makes sense to have this spillover, this bias term. So concluding, is it adaptive to be biased by your mood? Yes, if there are correlations between the actions that you can select and if there are autocorrelations in the environment. Now, This is definitely true for the seasons, and we all know that there are seasonal changes in the abundance of fruits and of prey. But this is even true in the world that we live in today. We know that stock markets are correlated in its stocks, and we also know that good things tend to happen together. For example, when someone gets his PhD, there tends to be alcohol and good food and so forth. Second answer is yes, it is adaptive to be biased by mood if your mood bias is not too large. That is, if you are extremely biased by your mood, you can give rise to this maladaptive behavior that we see in phenotypes like depression and bipolar disorder. In the empirical work that I did, I've only focused on one of the two formulae of our theory. I haven't focused on the learning bit, I've only focused on the decision-making bit. But throughout our empirical work, we confirmed the existence of this mood bias in the general population. That is to say, across different methods of inducing affective states, which were all confirmed, and also when moods fluctuate naturally. Secondly, we find this when we apply different kinds of choice tasks, different kinds of costs that each time were incidental to moods. Now, clearly in our empirical work, there was no relationship between the decisions that people made and the moods or emotions that we induced. So you could argue that in that case, it is irrational for our participants to have that influence on their decision-making, which kind of shows which kind of underlines our argument that this predisposition might have been evolutionarily inherited. Obviously, we haven't answered all questions that there are to be raised about this mood bias. And the first big open question that we have is, what is the neural basis of a mood bias? I'm currently still in the process of collecting data on epileptic patients who are treatment resistant. These people do our experiment while they are in hospital, and they are in hospital because they're going to get a resection of the origin of their epileptic seizures. During about 2 weeks that they spend in hospital, they have electrodes implanted in their brain. And since epilepsy is often temporal, we have a very good coverage of regions like the amygdala, hippocampus, and insula, that are regions that are implied or involved in emotions and also in decision-making. So we ask these people if they're willing to do a shortened version of our experiment, and they often say yes. And so they do the vignettes and emotion study, the vignettes and music study in a shortened version in their hospital bed, and we record the signals of these interesting brain regions. But this is an ongoing project. It's quite a bit of analysis work still to do. So that is an open question still to be answered. And the second question is whether the moods that we studied in the lab extend naturally to the moods that people report who suffer from psychiatric disorders, from mood disorders. And so the open question is to which extent our work, specifically our mood model, our mood theory, can be informative to people suffering from mood disorders. And that question is one that I will hope to answer during my postdoc. With that, I would like to conclude, and there are many people that I should thank. I will address you personally after the interrogation. For now, I will give the floor back to the jury, and thank you for your attention.